Dear students, we are going to look at the first law of thermodynamics applied to closed systems. Look at this question, which was asked in GATE Aerospace paper 2009 for 2 marks. After attending the first 15-20 minutes of this lecture, you will be able to solve this question. So let us see what are the things that we are going to discuss in this lecture. First, we'll look at Joule's experiment. Then, what is first law of thermodynamics? First law of thermodynamics applied to closed and stationary system. We will solve 3 questions which were asked in GATE exam. Then we will apply the first law of thermodynamics to isolated system. Then first law to a cyclic process. And then finally, we are going to understand what is PMM1, perpetual motion machine 1. So let's start. At the beginning, I'd like to ask you a question. Can you recognize this device? Do you know what this is? Well, this device is the Joule's heat apparatus, which Joule used to perform a series of experiments which laid the foundation for first law of thermodynamics. So these experiments were done by Joule in the mid 1800 centuries, that is almost 200 years back. And that is the time when the first law was first formulated. Now, why it is important to understand Joule's experiment is because before Joule did his experiment, heat was considered to be an invisible fluid known as caloric. And it was considered that this heat, right, which was a fluid, it flows from a body at higher caloric to a body at lower caloric. Now, Joule, with his experiments, proved that heat is not actually an energy, it is not actually an invisible fluid. Basically, it is energy in transition. And Joule's experiment laid the foundation to the first law of thermodynamics. Let us quickly understand what did Joule did in his experiment. So this is the Joule's apparatus, what you can see in the picture. So a rotating paddle was attached with a pulley, as you can see, with a mass. Now, when the mass was lowered, the paddle wheel rotated. So through this mechanism, Joule was able to transfer work into the system, which was isolated, not isolated, insulated. And the amount of that work that has been transferred can be calculated by how much the mass has come down, because we know that energy can neither be created nor be destroyed. So the decrease in potential energy will be equal to the work transferred into the system. And that is done by the rotating of the paddle wheel. Now, what Joule noticed, because the system was insulated, right, the temperature of the system started rising. So what it means that we can increase the temperature, means we can increase the energy of the system by work transfer. And then what Joule did is that he removed the insulation. And as soon as the insulation was removed, the heat transfer started, right? The heat started flowing out of the system, and the temperature which was increased, it came down to its original temperature. And Joule showed that this heat is proportional to the work done. So through his experiments, he showed that the energy of the system can be increased by 2 ways: by performing work or through heat transfer. Hence, heat is not a form of energy. It is basically energy in transition. Having understood the Joule's experiment, let us try to understand what is first law of thermodynamics. Now, first law of thermodynamics is nothing else. It is simply conservation of energy, which we have been listening to, which we have been learning since our younger days. That energy can neither be created nor be destroyed. It can only be converted from one form to another. Let us try to understand what is first law of thermodynamics. Now, mathematically, the first law of thermodynamics can be written as the change in energy of a system is equal to heat transfer minus work transfer. Let us try to understand this equation. Let me say I have a system. It could be any kind of system, right? And suppose I'm supplying some heat into the system, and the system is also performing some work. So there is some amount of energy in and some amount of energy out. By simply applying law of conservation of energy, I can say the change in the energy of the system is equal to energy in minus energy out. And simply this can be written as change in energy is equal to total heat transferred into the system minus total heat transferred out of the system. Now, it is not as simple as this. Let us try to make it a little bit complicated and relook at the first law of thermodynamics. Now, suppose there is a system and multiple heat transfer is happening and multiple work transfer is happening, as you can see in the picture. Let us try to plot it in a diagram. Let me say I'm using a PV diagram. So initially, before the heat transfer had started, the work transfer had started, let me say the system was at point 1. This was the initial state. Of the system. Now all different types of heat transfer has taken place, all different types of work transfer has taken place. As a result, what happened? The state of the system changed. Let me say the system moved from initial state 1 to a final state 2. Final state. So this is the direction of the process. Now what can I say that what is the total energy transfer? Total energy transfer, or instead of saying total energy transfer, let me say what is the total energy change of the system. So the total energy change of the system, how much energy of the system has changed, I can write it by the final energy of the system minus initial energy of the system, isn't it? So this is the change in energy, delta E. According to first law of thermodynamics, this is equal to the net heat transfer. So what are the heat transfer happening? Q1, Q2 and Q3. So I'm saying Q1 plus Q2 minus Q3. Why did I say minus Q3? Because last lecture we have learned that when heat is transferred to the system, into the system, it is flowing into the system, it is considered positive. So this is going to be positive. This is going to be positive. But when the heat is transferred out of the system, we consider it to be negative, right? Similarly, I can say total energy change is equal to total heat transfer minus total work transfer. So what is the total work transfer? Total work transfer, I can write it as W1 plus W2, or if I actually take it with the sign convention, I will not write W1 plus W2. Instead, I will write W1 minus W2. We'll talk about it in some time, plus W3 plus W4 plus W3 with a bracket definitely plus W4. Now why we have taken plus and minus? Again, we have seen it in last class that whenever work is done on the system, we consider it to be negative. And whenever work is done by the system, we consider it to be positive. So the sign convention is very, very important if you really want to solve questions using the first law. So if you summarize this point, it can be rewritten as change in energy of the system is equal to the net heat transfer minus net work transfer. So this is nothing else but the first law of thermodynamics. Now, if we apply this to closed and stationary system, now we know that what is delta E, right? We have seen it in our last class that delta E is equal to change in internal energy plus change in kinetic energy plus change in potential energy. This is the total energy of the system. But for closed and stationary system, can I say the change in kinetic energy and change in potential energy will be equal to 0 if the systems are stationary, right? So for closed and stationary system, we can simply say delta E is equal to delta U. So how can I write the first law of thermodynamics? Now delta E changes into delta Q. Sorry, not delta Q, delta U. Delta U is equal to net heat transfer minus net work transfer. Sometimes this law is also written like this. We take the work transfer to the right hand side. We can also write it as net heat transfer is equal to change in internal energy of the system plus amount of work done. Always keep it in mind whenever you are applying this law, you have to take the sign convention of heat transfer and work transfer according to what we have pre-decided. Having understood this, let us try to attempt a simple question which was asked in GATE Mechanical 2004 for 1 mark. Let us read this question. And please try to attempt the question in the same fashion, right? The process of attempting a question is very, very important. A gas contained in a cylinder is compressed. So we are going to draw the diagram. Whenever a diagram is possible, try to draw the diagram because it helps us in understanding the process better. Now, as you become expert in this, slowly you will be able to do even without solving, without drawing the diagram. Cylinder is compressed, work required for the compression being 5,000 joule. Now the cylinder, you have gas inside the cylinder. Now it is being compressed. So if it is being compressed, what it means, work is being done on the system. Right? Work is being done on the system, and whenever work is being done on the system, we will consider it to be negative. During the process, a heat interaction of 2000 joule causes the surrounding to be heated. So the surrounding is getting heated. So if the surrounding is getting heated, what it means that there must be heat transfer out of the system, Q. And whenever heat is transferred out of the system, again, we consider it to be negative. So let us write down the numbers, numerical values that are given. So work transfer is given as 5,000. We know that it is negative. So negative of 5,000 kilojoule. And heat transfer, net work transfer and net heat transfer, I'm writing it as delta Q and delta W, is equal to minus 2000 kilojoule. It's a very, very simple question, and that's why it was being asked for only 1 mark. According to first law of thermodynamics, right, what we need to answer, we need to find out what is the internal energy. So what is the internal energy? Change in internal energy is equal to heat transfer, net heat transfer minus net work transfer. So I can write it as minus of 2000 minus of 5,000. So this is equal to 3,000. And since the unit we have taken is kilojoule, so final answer will be 3,000 kilojoule. Answer is C. Very basic question, but if anybody doesn't know how the signs of heat and work are taken, there's a very good chance of making a mistake in this question. Now let us take a little bit advanced question, a level above question, right? Again, this was asked in GATE Mechanical 2011, right? Mechanical 2011. Now thermodynamics questions, the basic questions are more asked in mechanical engineering than in aerospace engineering, but we have to understand the concepts properly, because though these are basics, we'll have to apply the advanced concepts when we are learning, right? The advanced topics like gas turbines, propulsion, all those things. The content of a well-insulated tank. So well-insulated tank, what can we say about this? Is a well-insulated tank. So the tank is insulated. So once I say that the tank is insulated, what does it mean? Insulated means no energy, no heat energy can get into. There cannot be any heat transfer. So net heat transfer has to be zero. Right? Is heated by a resistor of 23 ohm. Now, let me tell you something. Many of the questions you will be able to solve it even without putting a pen down. See, the net heat transfer is zero. So definitely I can eliminate option B and option C. Why? Because you can see here the net heat transfer is not equal to zero here. So definitely option B and C cannot be the answers, right? Because the tank is well insulated. Now, there is a resistor, and the resistor is heating the system. So we have a resistor here, right? And the resistance of the resistor is given to be 23 ohm, right? And there is a current flowing into the resistor which is equal to 10 ampere, right? So because of this, the system, right, gets heated up. The work done by the system and the heat transfer to the system are positive. Okay, this is something we already know. The rate of heat, work, and change in internal energy during the processes. Now, even if we don't solve it, okay, just by analytical approach, can we solve it? Let us see. Now you see, the heat is getting transferred into the system. No, sorry, I'm very, very sorry. Heat is not being transferred into the system, right? But the internal energy, current is flowing, the resistor is getting heated up, right? So what will happen to the internal energy of the system? Will it decrease or will it increase? Definitely, I can say that the internal energy is going to increase because current is flowing, the resistor is getting heated up. So definitely the internal energy is positive, right? So if you see the other two options left, in one option, internal energy is positive, in one option, internal energy is negative. So definitely I can eliminate option D also, right? So even without solving this question, I can say the correct option should be A. Now let us try to see. Right? Now can you tell me what will be the change in internal energy? Now the change in internal energy is given by I square R, right? This is the heat produced by the resistance of the resistor, right? So if you calculate this, this is coming out to be I square means 10 square into resistance is 23. So this is going to be 2300. Now please understand this, this will always be in watt, right? This unit, the unit of this is watt. What is watt? Watt means that is joule per second. This amount of heat, 2300 joule of heat is being released by the resistor per second. So if you convert it into kilojoule, right? So it is going to be 2.3 kilojoule per second, that is kilowatt. Now, if you apply the first law of thermodynamics, we know delta U is equal to delta Q minus delta W. So delta U we have already found out, that is equal to 2.3. Delta Q is 0 minus delta W. So from here you can see delta W is equal to minus 2.3 kilojoule. So even through this we can clearly see that our correct answer is A. Now what is the meaning of this minus sign? The meaning of this minus sign is that work is done on the system. Now some of you might get confused, sir, but it is said that it is heated by the resistor. Yes, the terminology heated is being used, but you have to understand that this is not heat transfer. Why it is not heat transfer? If you remember the definition of heat transfer from our last video, right? Heat transfer is the energy transfer because of temperature difference between the system and surrounding. But since the insulation, because of the insulation, no heat transfer can take place. This anything except heat transfer is known as work transfer. So basically, though the resistor is getting heated, the resistor is placed inside the tank, and we will consider it to be work. Precisely, this is known as electrical work. Now let us look at the question which was asked in GATE AE, aerospace paper, in the year 2009 for 2 marks. So in this question, as you can see, a piston compresses 1 kg of air inside a cylinder as shown. The rate at which piston does the work is 3000 watt. Again, you can see here what is being given is the heat work done, right, is given in terms of watt. So what is watt? Watt is 3000. This is, I'm saying 3000 watt. That is equal to what? 3000 joules per second. Now, because the piston is doing the work on air, I will say this is negative because work done on the system is considered to be negative, right? At the same time, the heat is being lost through the walls of the cylinder at a rate of 847.5 watt. So what is heat transfer? So it is given as 847.5 watt. This is equal to 847.5 joule per second. Again, heat is being lost, right? So work is being done into the on the system and heat is being lost. So I'm going to consider heat also as negative. So this sign convention is very, very important. Otherwise, you'll not be able to come up with the right answer. Right? So what is the net change in internal energy per second, right? So whenever I'm considering rate, just one thing that you need to do is we will denote it as delta U dot. So whenever I'm writing dot, it means it is per second. Rate is given, right? So change in internal energy per second is equal to amount of work heat transfers per second minus amount of work done per second. So what is the change in internal energy per second? I can write it as minus 847.5 minus of 3000. So if you calculate it, it will come out to be plus 22,152.5 joules, or in fact, if I want to write it in watt, right? Or we can directly write it. Now we know that it is nothing else but joule per second, right? So in 10 seconds, what will be the change in 10 seconds? In 10 seconds, total change in internal energy, right, is equal to 2152.5 joule per second multiplied by 10. So this is coming out to be 21525 joules. Now, as we have considered unit mass here, right? So it will be joule per kg. So the final answer will be A. Very, very simple question, right? For 2 marks. Having understood this, let us try to define the first law for a closed system properly, right? So in general, we write change in energy of the system is equal to heat transfer minus work transfer. We can also write it like this, right? If you simply take work transfer to the right, we can write heat transfer is equal to change in internal energy plus work transfer. For stationary system, the delta E changes into delta U. per unit mass. So per unit mass means we are simply going to, this is specific properties, right? This will be specific energy, right? This will be specific energy. We are simply dividing it by, mass, and in the differential form, this is how we can write it for small amount of heat transfer, small amount of work done. So this is the basic. Everything is the same thing, just we are writing it in different forms. Now, if we take an isolated system, now what is an isolated system? For an isolated system, we know it does not interact, the system does not interact with the surrounding, means the net heat transfer and net work transfer are going to be zero. So if we write delta E is equal to delta Q minus delta W, right? We know that since the heat transfer and work transfer are zero, the change in energy of the isolated system will be zero. Always remember, if we are considering an isolated system, the internal energy of the isolated system, the energy of an isolated system will always constant. Now, can you give me an example of an isolated system? Well, a very good example of an isolated system is the universe. Because the universe, just think it. The universe, if it exchanges heat, with whom is it going to exchange heat? Right? The universe is whole, right? As one thing, right? There is nothing except outside the universe. So if we apply this, we can say the energy of the universe remains constant. Now, having said this, let us try to understand what is the first law. How can we apply the first law for a cycle? Now, say the system, it was initially at point 1. This is the initial state, right? That it underwent a process, it went to point 2, right? So in this process, there was some amount of heat transfer, there was some amount of work transfer, right? And it went to point 2. Now, again, it goes from point 2 to point 1 through another process, A. Again, in this process, there will be some amount of heat transfer, some amount of work transfer. I'm not considering any magnitude, I'm just telling you, right? And it reaches point 1. Now, when it reaches point 1, once again, we can say the energy of the system. What is the energy of the system? The change in energy of the system is equal to, instead of saying E2 minus E1, right? I will say it is initial energy and again final energy, right? The final energy and initial energy are the same because it is again at the initial state. The energy of a system is a point function, is a property of the body, right? At point 1, so I can say the energy final is equal to energy initial. So what is the net change in energy? Net change in energy is equal to 0. So now if I write down the first law is equal to change in energy of the system is equal to amount of heat transfer minus amount of work transfer. Now, if this becomes 0, so heat transfer minus work transfer is 0. So what I can say that amount of heat transfer is equal to amount of work transfer for a cyclic process. Now, this is going to help us a lot when we understand the cycles later on. So we'll be able to calculate what is the work transfer, the net work transfer by simply calculating what is the heat transfer. It is easy to calculate the heat transfer than calculating the work transfer because of the equations that we have. So whenever you are doing a Brayton cycle, whenever you're following a cycle, Brayton cycle is a cycle which is used in the gas turbine. So we'll be able to calculate what is the work transfer by simply calculating the heat transfer. And slowly, in some of our future classes, we are going to learn how to calculate the heat transfer for different processes. Having understood this, let us summarize some of the points, right? Some of the observations of first law. First of all, the first law cannot be proven mathematically, right? It is an experimental law which has been observed through experiments. Until now, it has been almost 2,000 years, sorry, 200 years since the first law was formulated in the 200 wars. There has been no violation of the first law, right? So it can be considered to be a very, very fundamental physical law of nature. Now, from the first law point of view, you understood that heat and work are the same thing. Heat can be converted into work, and work can be converted to heat. In cyclic process, net work done is equal to net heat transfer. Right? So, first law does not differentiate between heat and work. And slowly, when you read second law of thermodynamics, that is when you'll understand that though the first law does not differentiate between heat and work are two different forms of energy transfer. Right? Heat transfer is different, low level energy transfer, whereas the work transfer is considered to be high level, high grade energy transfer. We learn all these things when we learn second law of thermodynamics. Finally, I'd like to conclude with perpetual motion machine 1. Now, perpetual motion machine 1 is a device, is a machine which produces work without any heat transfer into it. Now, it violates the first law of thermodynamics, but because how can it produce energy without consuming any energy? Now, why it is studied, why it is important to mention it here? Because there were many scientists who proposed some machines which fall into this PMM1, perpetual motion machine 1. And those concepts, those machines were not even studied, not even considered, right? Because it violates the first law of thermodynamics. So it is very, very important to understand that. So it is very, very important to understand what not to study than what to study. Because we know that first law of thermodynamics cannot be uh, violated. So if anybody proposes a machine which violates the first law of thermodynamics, it's better to not pursue it, not to further try to develop it.